Hello students, right, welcome to reaction mechanism. As promised during our lecture on 15th February, I wanted to review selected pages of the lecture notes, but we didn't have the time during the lectures because the bulk of the lecture was focusing on activities 3 and 4. So I thought I will create this particular video to showcase to you some of the main ideas which came out from those two activities. Okay, yeah, but before we move on to the relevant pages, I thought I just want to share with you the learning outcomes which are being abstracted from the SEAB website on H3. Okay, so you notice that there are two broad categories of reaction which you need to be familiar with. One is nucleophilic substitution, and for nucleophilic substitution, if you tie it to activity 4, some of these terms you should be quite familiar with. For example, part A, explain how the relative rates of nucleophilic substitution is affected by the nature of the nucleophile, which we talk about it, the leaving group and the substituent, or what we call it as the substituent effect. And I did mention that solvent effect is not in your curriculum, but they can give you some data and ask you to make some deduction based on the data. Okay, so solvent effect is not in your curriculum because it's not written here. And then for part B, describe and compare the mechanisms kinetics for SN1, SN2. If you recall what you have gone through in your H2 notes, it's quite similar, except that for SN1 you need to have a brief understanding of steady state approximation. Okay, and then in terms of stereochemistry, you also need to know about the ion pair interaction for SN1, which I guess you have heard of me talking about it during one of the review videos on activity 4. Okay, and I think it was mentioned very explicitly here that the solvent effect is not required. Okay, so just take note of it. And then for elimination, which is the second broad mechanism you need to know, I think I will talk about it when we reach the relevant page, which are pages 30 to 40. Okay, elimination is the only part which we did not cover in our activities, so I thought I will run you through some of the main contents in the notes. There is also another very important mechanism which wasn't quite mentioned in the learning objective, but they often test it. That is known as addition elimination, or what we commonly call nucleophilic acyl substitution. Yeah, so we will cover that in the remaining portion of the notes from pages 42 onwards. Yeah, so just stay focused on that. Okay, so without further ado, I will move on to talk about the mechanism aspect, which is from page 8 onwards. Okay, yeah, so if you could flip over to page 8, now I will talk about page 8 to about page 15, briefly just run you through some of the main ideas. I'm not going to like go through with you page by page like what I normally do for H2, but I thought I just want to show you some of the broad ideas and some of the stuff which you shouldn't be, some of the mistakes which you shouldn't be making. Okay, so mechanism is there are two broad categories you need to know for H2. Radical based. The only thing you know about radical based is free radical substitution. Yeah, anything beyond that, I think we need to guide you with some guiding phrase so that you can draw the mechanism. Yeah, so free radical substitution is the only one you need to know for your H3 exams, at least off your memory. And then for polar ionic reaction mechanism, these are stuff which you should be very familiar with from H2. In case you forget, I can just summarize it for you. What you need to know is electrophilic addition, that is for alkenes, and then electrophilic substitution, that is for arenes. Nucleophilic addition, you probably have not studied that. That is under carbonyl compounds. Okay, so particularly ketones and aldehydes. Okay, and then the final one will be nucleophilic substitution, which you are familiar with from the chapter on halogen derivative for H2, as well as what we have gone through for activity 4. Okay, so yeah, so these are just some of the brief ideas they mentioned to you. I think you can go through them on your own. As to the definition of nucleophiles, electrophiles, you should be familiar with from H2, so I don't think I want to bore you with the details, but do be reminded that when you start to draw your mechanism, it's always pointing from a nucleophilic site, or we can call it a nucleophile, which could be a lone pairs of electrons or a pi bond. It needs to be pointed towards an electron deficient site. Yeah, and in the language we use for H3, we will call an electron rich site as an electron source and an electron deficient site as an electron sink. And when you push electrons, you always push it from the source to the sink. And when you do that, most of the time you will not be committing unnecessary mistakes. Okay, so electrophile is something which you should be familiar with, so I don't think I need to discuss that. This is an example of a polar reaction where a nucleophile, being an electron source, okay, over here, is pointing towards an electron sink. Okay, so you can also call this electron source, okay, which is the lone pair, and this is an electron sink. Okay, a very classic example of pushing electron densities from source to sink is some form of a conjugate addition. So for example, if let's say I have cyanide, okay, with the lone pairs of electrons on carbon as the electron rich site, and then we have a series of conjugated alkenes, and then you notice that the delta minus at the oxygen here is what we call an electron sink. Yeah, because it is the sites where negative charge can be stabilized. Yeah, so potentially the lone pairs on cyanide can attack 3 potential sites. Okay, so the first site it could attack is the carbonyl carbon over here, and then when it attacks here, the pi bond will break towards the electron sink. Yeah, so so when we push arrow like this, I think you can understand that the lone pair is what we call the electron source. Okay, the electron source here, and the C11O, the carbonyl carbon, is the electron sink. Yeah, because it's the one that is electron deficient. And then the pi bond now is the electron source again, and then the electron density gets pushed towards the electron sink, which is the oxygen, and it prefers to take on the negative charge. Yeah, so broadly speaking, you push electron density over from the source to the sink. So the source is the lone pairs of electrons on cyanide, and then the electron sink is the oxygen on the carbonyl group. Yeah. This is one example. Another example you could look at is I could push it from the electron source to this particular pi bond. Okay, and the electron density gets pushed towards the sink, so the pi bond breaks to form another pi bond, and then the CO pi bond break towards the oxygen. And then if I input the delta plus, delta minus, I think from here you can see that the carbon, which I'm going to highlight in green, is what we call potential electron deficient sites. Okay, yeah. So if I'm going to continue further, I'm going to put a delta minus, delta plus here. I think you can tell that the other carbon right at the end is also an electron deficient site. So if we try to push from source to the sink, this is what we will be getting. Okay, so I'm going to showcase to you. So go from the source to the sink, source to sink, source to sink, source to sink. Okay, yeah, so in general, when you push arrows, you normally go from one end to the other end like this. Yeah, you realize that the arrows does not converge, it diverge. Okay, so it move away from the source. You don't go from source to source. Like two sources don't attack each other because they will undergo significant electronic repulsion. Yep, okay, so I have to spend a little bit of time here because normally when students do arrow pushing, they tend to have more than 8 electrons in one of the carbon atoms or nitrogen or oxygen. So you have to be really careful about this. Okay, then another term we often use is living group. I think this needs no introduction. Okay, so I'm just going to skip this. Okay, so these are some guidelines in drawing reaction mechanism. We were thinking the best word to use here, because these are not rules, they are also not like postulates, they are not gospel truth, you see. Yeah, so the guidelines are not exactly meant to be followed from like page 18 or page 10 to page 13. That's not supposed to be the way. I think the main thing here is that we are just trying to showcase to you some of the usual things which you need to take note of. You shouldn't be memorizing them, but I think it's more of understanding that these rules or these guidelines are there to guide you towards drawing a more likely mechanism rather than a mechanism that is less likely. Okay. Yeah, so I think the first thing we need to understand is that there must be mass and charge balance. So meaning whatever you have on the left, you must end up, and then you should end up with whatever you have on the right. And then if the total charge on the left is neutral, the right hand side must be neutral. If total charge on the left is -1, right hand side must also be -1. Okay, and then you notice that it does make sense because now, for example, in this particular reaction, is a methoxide abstracting a proton from hydrogen bromides. So when the O- grabs the H, it grabs it as a H+. So there's a polarity difference between H and Br. Yeah, and Br being the more electronegative element, then H, it will be the electron-rich site. So it will be the one that is preferred to take on the extra negative charge. Yeah, so the negative charge is pushed to grab the H, and then now it's neutralized, and then the bromide now becomes the one with the negative charge. Okay, yeah, and then there's also the one which you should be familiar with from nucleophilic substitution. Yeah, so for ammonia, there's a lone pair of electrons on nitrogen, and ammonia is neutral, but because it has the lone pair is now available to coordinate to an electron deficient site. So you undergo nucleophilic attack on the carbon bonded directly to the Br, not the other way around. And because of that, the bromo group leaves as a bromide over here. Okay, and then your ammonia becomes ammonium, or what we call the conjugate acid of methylamine. Yeah, so the nitrogen will take on a positive charge, and because of that, it being a conjugate acid, one of the H here can be easily lost to say another ammonia molecules. So I can expect another ammonia molecules to grab the H and then neutralize this charge, and then together ammonium bromide will be the byproducts. Okay, yeah, so so and so forth. So I guess you need to go through some of these on your own. Really not meant for, I shouldn't be the one going through all the details. And then of course the octet rule, very important, because remember that period 2 elements, especially carbon, nitrogen, oxygen, they cannot hold more than 8 electrons. Okay, the very least nitrogen can have 7. Okay, nothing more, nothing less. Or rather, nitrogen can have 7 or 8. Yeah, but definitely not more than 8. Okay, when you draw arrows, right, it has been established by IUPAC. I think this is a rule which has been around for many years, since chemistry as a discipline formally gets set up. We start off the arrows from electron-rich sites, and then we end off the arrowhead towards an electron-deficient site. Yeah, and the arrow simply means electron pair movement. So do not reinterpret the arrow on your own. Yeah, do not think that the arrows means the movement of atoms. Yeah, because if you want to reinvent the rules, then it's very difficult for you to communicate your ideas on paper with other chemists. Okay, of course, unless you can make radical changes when you become someone famous. If not, I think the rules will still hold. Okay, and I think you can continue just going through some of the basic ideas, and I think you should be able to understand what we are trying to say. Okay, and of course for the fourth point, do take note of the medium. Yeah, so for example, in an acidic medium, it is unlikely that a negative charge species can live, because that species will likely be a good base. Yeah, so in our case here, for example, the ketone, this propanone, right, will be protonated in the presence of H+. Yeah, and after that you'll form the conjugate acid, and then the water will attack the electron deficient carbon. This particular step is crucial because water is a poor nucleophile. So in that case, this is very unlikely because water being a poor nucleophile, right? The first step is likely to have an extremely high activation barrier. Because being a poor nucleophile, it cannot attack a not so electron deficient site such as a carbonyl carbon. And then in the process, being in an acidic medium, right, you can't exactly generate a very strong conjugate base like an alkyl site. Yeah, so all this will sort of like break this particular rule, so you have to be aware of the medium which the reaction is taking place in. Okay, so this is important. I think point number 5, intramolecular reactions are often faster than intermolecular. So the example which I often used during lecture is like it is easier for you to slap yourself as compared to your friend slapping you, because your hand is directly bound to your body, and of course when you slap yourself, it's analogous to an intramolecular reaction. Your friend slapping you, it's analogous to an intermolecular reaction. Okay, so if you use that analogy, you probably understand why intramolecular reaction generally happen much faster. And this is also the basis of catalytic reactions. Like reactions, when you have a catalyst, generally the catalyst is able to hold the two molecules as though they are one singular species, and the reaction will therefore be more intramolecular-like than intermolecular-like. Okay, the number 6 guideline is what I often share with the students as well. It's good to number the carbon in your carbon skeleton so as to keep track of how the group shift, especially when there are rearrangement reaction. Yeah, I mean, if there's no rearrangement, like a normal SN2, SN1, nucleophilic addition, substitution, elimination, all this is easy. You do not really need to number the carbon. Yeah, but in reaction where it involves like relatively huge changes to the carbon skeleton, it is important to number the carbon so that you understand how the structure changes before and after. Okay, so that will help you keep track. I think this example helps you. It will be good to write a summary as well, to take note of like what exactly is happening. Yeah, so am I breaking a CO pi bond? Am I forming a sigma bond, or etc.? Yeah, so if you are able to number it, then I think it is easier for you to keep track. So for example, in our case here, it goes from left to right. So after I number the carbon, I notice that one of the methyl group, so that's carbon number 7, right? It gets shifted to carbon number 5. Yeah, so there is a shift, and of course the carbonyl oxygen directly bonded to the carbonyl carbon, which is carbon number 3, it's protonated. Yeah, so if we take reference from our earlier example, like for example here, right, you know that the first step probably involved the protonation of the carbonyl oxygen. So when that happens, let me just illustrate the mechanism for you. So when that happens, right, the carbonyl oxygen will be protonated like this. Okay, so the first step is I'm going to get a protonated carbonyl oxygen like this. Okay, with a H here, and it should be taking on a positive formal charge. Yep. And then the next thing that you might be aware of is when we look at how the pi bonds are being formed, you notice that C3 and C4 forms a pi bond, C4 and C5 the pi bond breaks. Okay, and then of course C5 and C6 the pi bond breaks as well, and then there's a new CC bond being formed between carbon 5 and carbon 7. Yeah, so the first thing that you might be wondering is, you might be doing this. You might be breaking the pi bond, okay, towards the OH. I guess that is what most of the students will do. Okay, again, I want to emphasize that there is nothing wrong if you are thinking about it in this particular manner, but I just want to emphasize on one little thing, some of the taboo in chemistry. Okay, so if you are thinking of doing it like this, you'll notice that I am forming a carbocation cation directly next to an electron withdrawing oxygen. Yeah, so my question to you would then be, will the protonated form be more stable, or will this be more stable? I think the answer is now obvious. I think you would agree that the form on the left is actually more stable. So in that case, it is therefore a taboo to draw something like this, because it's probably not going to exist. Okay, then if that is the case, then what should I be drawing? Okay, so then we should be thinking about this. When the pi bond breaks, how about another pi bond breaks like this? Okay, because we want to form a carbocation at carbon number 5 in order to allow the methyl group bonded to carbon number 6 to be shifted to carbon number 5. Okay, so what you are probably getting will be something like this. Okay, like this, and then with a carbocation here. Yeah, I hope you can see that this does make a lot more sense, because now I'm getting a secondary carbocation, and because of that, then I can expect the methyl group to shift towards this particular carbon. Okay, or if I want to draw it out more convincingly, then maybe like this. Yeah, towards this particular carbon. Okay, and then after that, I'm going to form this OH with pi bond here. Okay, you might be wondering why a methyl shift happens here. Because in this case, I am generating a more stable carbocation from a secondary carbocation to a tertiary carbocation. Okay, and because of that, right, what happens here is that I want to restore the aromaticity, because I could potentially end up with an aromatic compound. So yeah, so in this case, what's going to happen here is that the H will be lost as a H plus, and eventually I'm going to end up with the product, which is essentially a phenol. Okay, like this. Yep. Okay, so I hope you are able to see the step-by-step drawing of the mechanism. So this is the more likely mechanism. Of course, some of you might argue that how likely is the secondary carbocation being formed? Okay, so in most cases, if you are more experienced, then you could actually skip the steps in drawing the secondary carbocation. That means that if you can already tell that this is going to happen, then I'm going to draw it like this. Then straight away I will end up with the tertiary carbocation. Okay, then you might be wondering again, how do you tell it should be like this? Well, if you imagine that this is a carbonyl group, electron withdrawing carbonyl group, right? Yeah, then I'm going to expect this particular carbon here to be electron deficient. Yeah, so this is a hidden or a masked electron deficient site, the one highlighted in I mean the one with a green highlighted part over here. So this is a masked electron deficient site. So if you are more experienced, then you could actually draw it straight away. Then of course the question is, so which is right, which is wrong? At the end of the day, you are proposing a mechanism. You cannot say for sure which is right, which is wrong. So unless there are more experimental data for you to so-called prove it. If not, then I think it is almost impossible to showcase what is right and what is wrong without kinetics data. You could only postulate the mechanism based on what you know at hand. Yeah, like your current knowledge. Yeah, so I think as long as it's reasonable, we will not mark you down. Yeah, this is something which you do not need to worry about. Okay, then it will be good if you can draw it like what I did earlier on, like step by step. Like if you remember earlier on, I started off with a secondary carbocation instead of a OH directly bonded to a carbocation, and I explained to you why. Yeah, so if you can draw it out step by step, then you will be able to tell which is less likely or which is more likely. Okay, again, keep your mechanism straight and simple. do not break too many bonds and form too many bonds at the same time, and do not do fragmentations and mess up the whole thing. Yeah, so anything that involves too many crossing of arrows is not likely to be correct. Yeah, then from pages 13 onwards, we showcase to you some of the mistakes which students are likely to make. So for example, it seems that there is nothing wrong with this. It seems that there's nothing wrong, but what is wrong is that the breaking of the OH bond is not being shown. Yeah, this is quite a common mistake which students will make. And then of course in the drawing of resonance structures here, it is very often that the students will draw like this. Yeah, so imagine that if you push it like this, right, this particular carbon will have more than 8 electrons around it. Okay, how do we know? Because there are already 2 H's. Yeah, there are already 2 H's there. So if you push like that, right, then the carbon will have 10 electrons around it. Yeah, which is obviously impossible. Yeah, so definitely I wouldn't advise you to do that lah. As in, because there's no real reason why you should be doing that. Okay, so yeah, so this is a more likely way of showcasing the delocalization of the electron density around the final ring. Okay, typical valencies, I think you can go through this. Usually carbon forms 4 bonds, nitrogen 3 or 4 depending, oxygen 2 or 3. So if nitrogen forms 4 bonds, then it will take on a positive formal charge. If it forms 2 bonds, then it should take on a negative charge. Carbon 4 bonds should be neutral, 3 bonds positive. Carbocation, can it be a carbon anion? Yes, as well. Okay, oxygen, 2 bonds with 2 lone pairs. If it forms 3 sigma bond, 1 lone pair, then it should take on a positive charge. Okay, and then yeah, I think this mistake you should understand why. Yeah, so when we try to draw something like that, then you know that it's impossible because there is no lone pairs on H+. Yeah, so in that case, the lone pairs of electrons on O should be the one attacking the H+ and not the other way around. And then you push electron density away from, I mean, towards the electron sink. In this case, the oxygen is the electron sink, and not away from the sink. Yeah, if you push it away from the sink, what is going to happen is that your oxygen will gain a doubly positive charge. Yeah, so this is a wrong structure as well. This is a wrong structure as well. The reason why I drew it in like the way I drew, right, it's because I'm trying to showcase to you a wrong structure. I'm not saying that this structure is correct. Okay, and sometimes students like to draw vague arrows. So for example, like this, there is, are you trying to say that the carbon, something breaks from there, or are you trying to say that the CO pi bond breaks? And then are you trying to say that the oxygen atom moves, or are you trying to say that the lone pairs of electrons on oxygen attacks the carbon on carbon? Yeah, so vague arrows is a crucial problems for students when they draw mechanisms. Okay, and in this case, too many steps at once. Yeah, so as I mentioned to you quite often, usually we don't draw the mechanism with many steps at once. Oh, okay, so I think there's a little typo here, so you might want to correct it. There shouldn't be a H. Okay, so sorry, I think I need to correct this using the black. Yeah, so that the H shouldn't be here, so just cancel it. Yeah, so this is an example what we meant when we said multiple steps at one time. So this is like a third molecular reaction. Yeah, so a third molecular reaction is not possible, or rather it's unlikely, because you want 3 entities to come together. So most likely you will begin with a rapid equilibrium to protonate the carbonyl oxygen, and then the alcohol will then perform a nucleophilic attack on the carbonyl carbon. Yeah, it is more likely to be the case rather than everything else comes together. Okay, yeah. Practice makes perfect, so please work on your tutorials, and of course you'll be good if you can stay ahead of the curve a little bit when you're reviewing organic chemistry in the next 2 to 3 weeks, even before your H2 lectures begin. Okay, yeah, so I think we are done with the review for the first few pages. The next part we're going to move on to is nucleophilic substitution. We have gone through this in our activity 4. Yeah, so I will not bore you with the details because they they are actually quite similar to what you have in your H2 notes, except for a certain portion which I'm going to highlight to you. Okay, yeah, so this is the same example of the cone I used to explain in the H2 lectures on what we meant by inversion or stereochemistry. Yeah, and I did mention in the H2 lecture series that for H3 we will very much love to use this double dagger symbol to represent transition states. Yeah, but of course, if you don't like the double dagger, you can don't use it. You simply just write transition state below here if you wish to. Okay, if not, then I think you can stick to using the double dagger. And remember that SN2 transition state needs to be drawn. You need to be familiar how it looks like. Okay, but maybe for the purpose of H3, right? In some cases, when the question is not directly asking you to draw a second order nucleophilic substitution, then the transition state need not be drawn. So it really depends on the nature of the question. So I urge you to read the questions carefully. We have gone through this in H2, yeah, the profile of SN2. So it's a one-step process with one transition state, no intermediate. Okay. This is probably something which we didn't get to discuss in H2, because in H2 we do not talk about RS configuration. Yeah, so what we want to emphasize here is that inversion of stereochemistry does not necessarily lead to assignment of the configuration of the carbon. So for example, some students might have the misconception that an R isomer will become S, then S will become R. But do remember that R and S, right, the assignment is arbitrary because it is dependent on the groups it's bonded to. So if you are using a nucleophile which is of not similar priority to your leaving group, then it is possible that in the course of a reaction, S does become S and then R does become R, but it is still considered an inversion. Okay, because your cone still turns inside out. Yeah, so again, if you are quite confused, then I think it is good to review. I think number one, the naming of RS configuration. Yeah, and of course number two, in the drawing of the mechanism of SN2. Yeah, as long as you showcase the rear attack which results in inversion of stereochemistry, I think that should be fine. Okay. SN2 in cyclic system is also something which we did not quite cover in H2. Yeah, but again, over here, let's say we have a cis isomer. Cis here means that in the cyclic system, the two substituents, methyl and Br, are pointing in the same side, meaning they point towards the top. And then upon nucleophilic substitution, especially in this case SN2, right? There's an inversion. So in this case, the cyanide now it's pointing downwards. So from a cis isomer become a trans isomer. Okay, this is not surprising. So I guess it's not something which you need to pay a lot of attention, but just be aware how you showcase your stereochemical projection. What I can say, the difference between H2 and H3 is that there is more emphasis on drawing of stereochemistry for H3, which is in closer reality to what you have in university. Okay, cyclic system tends to react more slowly due to ring strain. Yeah, so I think this probably needs no further introduction. Yeah, so you can go through this on your own. Okay, unimolecular nucleophilic substitution, SN1. Okay, so similar to H2, you have a slow step, which is a equilibrium reaction between a carbocation and the substrate, and then you have a fast step involving the nucleophile directly attacking the carbocationic intermediate. Okay, so again, the details are here. In most cases, we agreed that we will end up with a racemic mixture. Okay, so there is no preference unless other factors comes into play, which we are going to discuss later. Okay, and of course for the energy profile diagram, there are two humps. Okay, there's an intermediate carbocation over here. Okay, so that is characteristic of SN1. Okay, next we are going to move on to steady state approximation in SN1. If you want to read out a little bit more, please do so at your own leisure, but for the purpose of H3, we are only covering it for SN1. So I'll give you a very brief introduction by moving back to page 19, where we showcase to you two elementary steps for SN1. Okay, so do take note that these two are elementary steps. Okay, so what do we really mean by elementary steps? So by elementary steps here, we mean that we are able to write out the rate equation for every single one of them, and we will be able to tell which are the species involved by simply looking at the steps, because the steps cannot be broken down further. Okay, so I'm just illustrating it for you. So in this case, the rates of consumptions of the substrates, okay, is simply equals to K1 multiplied by the concentration of the substrate, and the molecularity is 1. Okay, so to the power 1. Okay, the rate of formation of the product, which is the alcohol, is simply equals to K2 and multiplied by the concentration of the carbocation raised to the power 1 and the concentration of the nucleophile raised to the power 1. Yeah, so this is what we can do for elementary steps. We can write out the rate equation directly for every single one of the steps. Okay, however, if you take a look at the intermediate over here, right, it is the carbocation. Yeah, so the carbocation intermediate, right, there are several steps which defines it. So for example, over here, in the forward steps, okay, it is the formation of the carbocation, correct? Okay, so over here, maybe I can write out. So for the formation of the carbocation, so I'm going to write it out as the formation of the carbocation. That means the change in the concentration of the carbocation, okay, is actually equals to K1 RCl. Okay, so I hope this is clear cut. Yeah. However, right, as the carbocation is being formed, it is also being consumed back by K-1 and forward by K2. Are you able to see that? Yeah. So in that case, the change in the concentration of the carbocation is a little bit complicated. Yeah, it is not as simple as what we have here and here. Yeah, so it actually involved 3 terms. Yeah, so I need to continue. Yeah, so first we have the formation of the carbocation, which is based on K1 multiplied by RCl. Okay, and then next we have the consumption of the carbocation, so we need to put a minus sign here. Yeah, so which is dependent on K-1, and then the concentration of the carbocation and Cl minus. Okay, apologies, there's no space. As well as the consumption of the carbocation in step 2, so which is minus K2 carbocations multiplied by OH minus. Okay, so this is the full equation which I'm going to write for the change in the concentration of the carbocation. Okay, so please remember this and do take note of this, because it will appear again in the box on page 21. Okay, so now I'm going to move on to page 21. Okay, but before that, I'm going to highlight one important ingredient, why steady state approximation is important and what exactly it is. Okay, so basically here we are saying that the intermediate, in this case is the carbocation, it will not appear in the rate equation because its concentration cannot be determined with good accuracy. At least that's back in the olden days. Okay, and over here, right, the proposal by the German chemist Max Bodenstein, right, is that the intermediate concentration is a lot smaller than the reactant, so the rate of change is very small and it can be assumed to be 0. Yeah, so this is a very important ingredient I need you to take note of, because on the next page in the particular box, we're going to show the derivation. In fact, I have shown you already. Okay, so in fact, if you recall, right, I have already showcased this to you. Yeah. The only thing I didn't show you is the equating it to 0, which I have explained to you on page 20. Why do we need to equate it to 0? Yeah, because of the steady state approximation. So the rate of change in the concentration of the intermediate is close to 0. Yeah. This has a very important consequence. Yeah, because after we rearrange the equation, so we make K1RCl the subject first, and then after that we make the carbocation the subject. We notice that the concentration of the carbocation, right, has a relatively complex relationship with RCl, OH- and chloride. Yeah. However, we do understand that step 2 is the fast step. Yeah. So if step 2 is the fast step, we would expect K2 to be much greater than K-1, and we would expect the multiplication of K2 with OH- to be much greater than K- with R and Cl-. Yeah. So because of that, this thing will tend, we will approximate the expression below to K2 OH-. Essentially, it's very similar to what you did in acid-base equilibrium. When you assume that the change is very small, so you assume that the equilibrium concentration of the weak acid is approximately the same as the initial concentration. And then eventually we are going to get this particular term. Okay, and do you remember that earlier on I showed you how to get the rate of formation of ROH? If not, then I'll just go back to over here. So the rate of formation of ROH is over here. And you notice that it is dependent on the concentration of the carbocation. So let us multiply in the concentration of the carbocation which we have derived. And this is what we get. So we're going to put this into here. Okay. And you notice that OH- gets cancelled out, K2 gets cancelled out. So we end up with a first order kinetics. So this is how you derive the rate equation for SN1. Okay. So I hope you do able to take note of this. This is the actual derivation of the rate equation for SN1. Then some of you might ask, oh, what if my K-1 is quite fast for some of the substrate? Yeah, then you're going to end up with a relatively complicated rate equation, which is the case for some of the actual reaction of some other systems. Okay, yep, so essentially this is the steady state approximation you need to know. If you want to have more examples, I mean, you can highlight, and we could probably give you more examples, but at least for the purpose of H3, you simply need to know this. Yeah, so I think you don't have to worry about any other things. Okay, then we'll move on to the stereochemistry of SN1. Similar to what we have gone through for H2, for SN1, because the intermediates carbocation, right, is trigonal planar in geometry. Yeah, like over here, right? So the nucleophile can approach from the top and bottom plane with near equal probability, giving rise to a racemic mixture. Okay, so you will end up with 50% of the top attack product and 50% of the bottom attack product. Some students will ask, is it always 50-50? Can there be like a 49-51? Of course, it is possible. Okay, it is possible. So we highlighted this ion pair interaction in our activity 4. For ion pair interaction, for example, the CCl bond is stronger than CBr in our case here. Yeah, so that means that in the intermediate, right, you would expect the Cl- after it leaves, right, it will still forms relatively strong interaction with the carbocationic intermediate. So you have something like an ion pair. So when you have an ion pair near the top, right, I think it is understandable that it will block the top attack a little bit. So that is why you end up with maybe the bottom attack product a little bit more as compared to the top attack product. So that is why in our case here, when you have chloride, you only get about 41% of the products being formed when the nucleophile approaches from the top. Yeah, but of course, in most cases, we are not able to predict ion pair effect. Of course, in our case here, you are given chloride, you are given some data, and this is how you argue your case lah. Yeah, so that is only possible if you have data. So without the support of experimental data, it is very difficult to conclude whether the ion pair effect will exist. Yeah, in our case here, we are quite confident because we do know that chloride is a poorer leaving group as compared to bromides, and at the same time, you expect its ion dipole interaction, in this case the formation of the ion pair, to be of significant strength, or to be more significant as compared to the ion dipole interaction, say between a bromide and the carbocation. Yeah. There's also another case which I briefly mentioned to some of you, so if you recall, but before that, maybe let me explain to you why SN1 produces a 50-50% if the other groups are non-chiral. Okay, so that is very important. Yeah, so first of all, right, we need to understand the transition state leading to the product. Okay, so when we try to draw the transition state leading to the product, right, I think it will look something like this, with a carbon here, and then like this, as well as this. Yeah, so this is the transition states leading to the products. Okay, in case you can't see the dotted line, so maybe I will want to use something a little bit more prominent, so it's the dotted line, so I need to use dot. Okay, so this is the dotted line leading to the product. Then I'm going to showcase another intermediate below. So this is the transition state leading to the product where the approach is from the bottom. Okay, so I'm going to draw the BR here, and then the dot. Okay, yeah, so this is the transition state leading to the product. So this is delta plus, delta minus. Yeah, I want you to take a closer look at the transition state, right? Do you notice that these two transition states are also in an enantiomeric relationship? So which means over here, right, we are getting an enantiomeric transition state. So enantiomeric transition state has the same energy as one another. So that means that there is no differentiation between the two. Yeah. The only, I mean, in most cases, you are able to get product differentiation, right? Because somewhere in your molecule, right, there is another chiral center. So either another chiral center or 2 or 3. Yeah. So if you have other chiral centers, right, you will notice that the transition states relationship is diastereomeric. So when the transition states relationship is diastereomeric, then there will be some difference in energy. Yeah, however small the difference is, right, as long as there's some difference, then there will be some preference. So the larger the difference is, the bigger is the difference in the product. So that is what leads to stereoselectivity in the course of the reaction. Yeah, but of course these are all knowledge which you probably need not know for H3, so you can, I mean, we can just leave it as it is lah. But if you are interested to read a little bit more about them, I think you can feel free to do so to enrich yourself. Okay, yeah, so I'm going to move on to 3.1.3 factors that affects the types, the rates, types of nucleophilic substitution. Okay, I will not attempt to like talk a lot about this because we have already gone through them in activity 4, and there's already an uploaded recording. So I will just briefly mention about the substrate effect. Yeah, so this is common. Tertiary will be the least reactive towards SN2, and then most reactive towards SN1, and then primary will be the most reactive in SN2 and least reactive for SN1. Okay, yeah. The little extra bit of knowledge you might want to be able to showcase your more profound understanding in drawing of resonance structures is, remember in H2 we say that when the halogen is bonded to a sp2 hybridized carbon, there's partial double bond character. Yes, how does the partial double bond character arise? So it's shown to you over here lah. Yeah, so you can use the drawing of resonance structures to showcase how the lone pairs of electrons on the halogen can delocalize into the CC pi bond. Okay, and then of course carbocation over here, why is it that a tertiary carbocation is more stable as compared to secondary? Okay, we also learn about the Harmon postulate. Okay, so this effect of the stabilization, if you wish to know, is known as hyperconjugation. Yeah, hyperconjugation. Okay, so in the words of molecular orbital theory, we say that the CH sigma bond, right, will partially interact with the empty p orbital, and in the course of this interaction, it will generate a new set of MOs. Yeah, and in this case, the new set of MOs being generated, right, the CH will be slightly more stabilized. Okay, so if that's something you wish to have an extension on, then you can read out more about it. Okay, and then in H2, we briefly talk about the fact that some primary substrate can also undergo SN1. Yeah, but we did not go into details how that happens. Yeah, except to say that, except to draw orbital diagrams to show you the stabilization of the carbocation. So, for example, in the case of H2, how do we illustrate this kind of carbocation, right? Is that we will showcase an orbital interaction diagram like this. Okay, and then with a carbocation over here represented in green. This is the empty p orbital. Okay, with a plus charge, and then we will share with you that because the empty p orbital is parallel to the CC pi system, so it will form a continuous overlap. Yeah, so this is actually okay for H2. It's not an issue, but for the purpose of H3, because you guys learn about the drawing resonance structures, so you are able to showcase something like this to tell us that the stabilization, right, will lead to the positive charge being spread out amongst the three carbon atoms, and because of that, the other carbon, or rather this particular carbon, right, will be a masked electron deficient site, where it is also prone to nucleophilic attack. Okay, sometimes this kind of reaction might not even undergo SN1. In certain cases, it is more likely that it undergo a kind of reaction known as SN2 prime. Okay, where it will attack from over here, and then this pi bond will shift, and then you kick out the chloride. Yeah, so whether it undergoes SN2 prime, we call this SN2 prime or SN1, right? You have to study the kinetics to see whether the nature of the nucleophile affects the rate of reaction. If it doesn't affect the rate of reaction, it's likely to undergo via SN1. Okay, and of course, we have more examples here. Okay, so you can read about them on your own. The nature of the nucleophile is also important. So the stronger the nucleophile, meaning the more polarizable, the better. Okay, so you can read through, because we have gone through all these extensively in our guided inquiry in activity 4. The nature of the leaving group as well. If the leaving group is a good leaving group, a stable leaving group, or a weak base, etc., then it can leave easily. Okay, so in our case here, the forward reaction is okay, but the backward reaction involving OH minus is the leaving group is not possible. Okay, yeah. Yeah, and in our case here, if we want our OH to be replaced by Br, we have to ensure that we convert the OH into a good leaving group. In this case, we need to protonate the oxygen, and then the OH will leave as water. Okay, solvent effects, I need to highlight this, not in the current H3 syllabus. Yeah, but we have gone through that in section D in our guided inquiry, so you can read about that. But here we focus on protic solvents, where solvents are capable of forming hydrogen bonds with the substrates or the nucleophile, and then polar aprotic solvents, in this case such as cyanomethane, DMSO. Yeah, so they are able to solvate the cations well, but they cannot solvate the anions well. We have also explained why that is the case in part D of activity 4, so please go and read up more about it. Okay, I don't repeat this because we have already talked about it in activity 4. Okay, so most importantly, the usual question we will ask ourselves for beginning students is that how do we know whether the reaction should be SN1 or SN2? Yeah, the true answer is we really don't know. We need to have the kinetics data. And then beyond the kinetics data, we also need to use some of our prior knowledge from our studies, and from there we can then make an intelligent guess whether is it SN1 or SN2. Yeah, but still, after we made that intelligent guess, we cannot say for sure that it is really like that. We still have to perform a kinetic studies, and from the kinetic studies we will then be able to tell if it's SN1 or SN2. Yeah, so this is the truth. Just to showcase to you and just to remind you, because we cannot just look at a reaction and then say for sure that, oh, this has to be SN1, this has to be SN2. Yeah, this is impossible. Okay, we have to have experiments to support our claim. Yeah, but we are able to say what are the factors which favors SN2. So for example, the substrate will be primary or methyl. We need a strong nucleophile. We must have a good leaving group, polar aprotic solvents. And then what are the factors which favors SN1? Of course, we must have a good leaving group. The protic solvent will be able to stabilize the carbocation. And then it needs to be tertiary because we need the formation of carbocation. Okay, so all these things, I think there are a lot of these in the discussion, and sometimes in Cambridge exams, school exams or A-level exams, we will ask you to use the different factors to sort of explain why a certain reaction showcase in the question undergo SN2 or SN1. Yeah, so from there you should be able to write out quite substantially. Okay, with that, we'll quickly discuss exercise 1. Okay, so in this case, the ethers can be prepared by SN2 reaction using alkoxides with alkyl halides. So if I want to produce this particular ether, which is a good route, I will prefer it to undergo. Yeah, you notice that both can give you the same product. Yeah, but route A will be the best. Why is route A the best? Because number one, right? Later on, you will learn that actually not only later on, I'm sure you have also encountered in H2 that substitution and elimination often happen hand in hand. Yeah, side by side. So if you want a substitution product, you cannot run away from an elimination product. Yeah, but in our case here, if we are using CH3I, right, then we will not run into the risk of having an elimination product. Yeah, the reason is because CH3I, there is no beta hydrogen for the base to abstract the H. Yeah, so therefore in route A, I can say for sure, almost for sure, that this is the only product I will get. Of course, there could be either minor product, but I mean very, very minor product, but we are not concerned with them. But for route B, right, we are running into the risk of getting an alkene as the side product. Yeah, so that is something you have to consider when you decide which is the routes you want the reaction to undergo to produce the product in good yield. Okay, then we'll move on to exercise 2. We are asked to rank each of the following reactions in order of increasing rates. Yeah, so again, our decision is number 1, right? They are all primary substrates. Okay, since they are all primary substrates, I'm expecting all of them to undergo SN2. Okay, so all of them will undergo SN2, largely SN2 . I'm not saying SN1 is impossible. Indeed, it's probably maybe very minor, but SN2 largely. Okay, so for SN2, we need to look at 2 factors. The nature of nucleophile, right? Yeah, so we understand that SH- is a better nucleophile than OH-. Yeah, and looking at the substrates, I am seeing a sterically hindered substrate here. Yeah, versus the other 2. Yeah, so taking into consideration the nature of the nucleophile as well as the bulkiness of substrate, I would expect reaction 2 to be the fastest. Yeah, so in this case, when I rank them, I will rank reaction 2 to be on the extreme right because it should be the fastest. Okay, followed by reaction 1. Yeah, because between reaction 1 and reaction 3, we are only comparing between the nature of the substrate. Yeah, is it bulky or is it not bulky? And then of course the most bulky substrate is 3, despite being primary, but there's a tertiary butyl group being attached to the CH2. Okay, so reaction 3 will be the slowest. Right? And then for parts B, I'm supposed to rank each of the following reactions in order of increasing rates. Explain your answer. So again, all of them are tertiary, so we're looking at SN1. Okay, now when we're looking at SN1, I think the first thing we need to understand is we need to have a good leaving group. And okay, my apologies, this should be TOS, like this. Okay, I think that will be better, but I think whatever we have written is fine. Yeah. So this is known as a tosylate. So a tosylate, you notice that if it leaves, it will leave as O minus here. Yeah. So we have two highly electron withdrawing S double bond O. So it will help to stabilize the negative charge to a large extent. So in that case, OTS is a very, very good leaving group. Yeah, so definitely reaction 3 will be the fastest. So when we rank them, reaction 3 will be the fastest. Okay, then what about between reaction 1 and reaction 2? Same substrate but different solvents. Yeah, so now the question is which solvent is able to form a stronger hydrogen bonds with the intermediate. Yeah, so which is able to stabilize the carbocation more. Okay, so in our case here, I would expect water being more polar, right, to be able to stabilize the carbocation more. So I'll expect reaction 1 to be in the middle. Okay, and then the slowest will be reaction 2. Ethanol, despite being a polar protic solvent, it can stabilize the carbocation intermediate, but in terms of the extensiveness of hydrogen bonding, it will lose out to water. Okay, then some of you might ask, didn't we say that OH minus is a poor leaving group? Yes, but we have HBr here. So the HBr being generated in situ, right, it will be able to protonate the OH, and then it will make the OH leaves as H2O. Yeah, because once the OH is protonated, you become OH2+. And then OH2+ will leave as H2O, and then form a carbocation which will undergo nucleophilic attack by bromide to give us the products. Okay, yeah. So with that, we have come to the end of the substitution. So it's the review of page 16 to 29 of the notes which we mentioned. Yeah, and the final bits of this particular review will be on elimination, which will take place from pages 30 to 40. Elimination is not new to you guys if you have gone through the H2 notes. So as a comparison, we look at the condition required to give us a nucleophilic substitution product involving sodium hydroxide. So we'll simply put sodium hydroxide heat under reflux. But for elimination, we will need to use ethanol as a solvent, or a mixture of ethanol and water. So we will call it ethanolic sodium hydroxide or ethanolic KOH heat under reflux. Yeah, so you have come across that in your H2 notes. So it's not something that's very new. Yeah, but what is maybe a little bit new here is that for elimination, you need to know the mechanism for H3. Yeah, so that's why we'll be discussing it here. Yeah, so similar to SN1 and SN2, elimination will also have two competing mechanisms, E2 and E1. So namely second order elimination and first order elimination respectively. And you probably guess that for second order elimination, the base will abstract an acidic proton, and in the process it will eliminate off the bromide group. And if you recall what was mentioned in the H2 lecture, right, we mentioned that between the CBr bond there is a bond polarity, so there's a delta plus here and a delta minus. And then if you move on, we will call the carbon the alpha carbon. So this is called the alpha carbon. The carbon next to the alpha carbon is known as beta. And because the alpha carbon takes on a partial positive charge, so it will induce a partial negative on the beta carbon, and at the same time the H bonded to the beta carbon, known as the beta hydrogen, will have a partial positive charge being induced. Yeah, so that makes it slightly acidic, or that makes the beta hydrogen slightly acidic. So in that case, if we have a strong enough base, we will effect elimination, and this is exactly what is happening here. And if you recall what I mentioned in the H2 lectures, I did mention that such elimination is known as beta elimination. So most of the elimination which you learn in H3 or which you will ever encounter in a higher 2 or higher 3 curriculum will be known as beta elimination. Okay, so there are two mechanisms, E1 and E2. They share the same rate equation as SN1 and SN2 respectively. Yeah, but you will notice that for E1, right, similar to SN1, the first step is a slow step, so you will generate a carbocation. Yeah, so between SN1 and SN2, in the fast step, for SN1, the nucleophile will approach the carbocationic carbon via a nucleophilic attack to give you the substitution product. But for elimination, the base will approach the beta hydrogen to give rise to the CC pi bond. But because that is the fast step, so it might be a little bit difficult to control or to differentiate the products between E1 and SN1. Yeah, so you will probably realize after you learn this particular topic quite well that SN1 and E1, they are quite difficult to be selective. Like if you encourage an SN1 mechanism, there is a chance that E1 might take place solely because for the rate determining step, solely because for the fast step, it involved the nucleophile and or the base. So in that case, because it's involved in the fast step, you can't exactly use the nature of the nucleophile or base to help you control. So SN1 and E1 will always be competing with each other. But for E2, it's a different story, because for E2, right, the base and the substrate occurs in the rate determining step. Yeah, so the nature of the base will cast a defining moment. Okay, so the nature of the base, right, will be important and in deciding whether you will get an elimination product or whether the substrate will prefer to undergo a substitution instead. Yeah, and over here you probably, I think along the way, even during our activities, you probably have heard of this term known as a non-nucleophilic base. That is a base that is a poor nucleophile, solely because it is directly hindered. Yeah. Okay, then so moving on, I think over here they mentioned a third possible mechanism. Yeah, so generate the carbon anion first, followed by elimination. This mechanism is not within the syllabus. This is known as E1CB, first order elimination conjugate base. I think I illustrate it in one of the activities. Yeah, so where possible, you can take a look at the exercise in activity 4, if I'm not wrong, or is it activity 3? Yeah, so that's E1CB. Okay, so bimolecular elimination or second order elimination is what we're talking about. It's happening in one concerted step, so you expect the transition state to involve the formation of the base hydrogen bond, and then as well as the formation of the CC pi bond, as well as the breaking of the C halogen bond. Okay, and you notice that in the course of reaction, right, there is an increase in number of moles of species. So from 2 species to 3. Yeah, so if you are looking at delta G equals to delta H minus T delta S, using the same condition, meaning that for example, I'm using the same base. The base can also be used as a nucleophile. Yeah, I could control the elimination product simply by increasing the temperature. Yeah, because elimination is entropy favored. Yeah, whereas substitution is almost entropy neutral, because in the course of reaction for substitution there is no change in amount of species, but for elimination there is usually an increase in amount of species. Yeah, so because it's entropy driven, temperature can help encourage elimination products. Okay, so the rate determining step, the rate equation will be similar to SN2. Yeah, and you would also expect that the transition state is what we have discussed earlier on. So again, the partial formation of the, in this case, the OH sigma bond, the partial bond breaking of the CH bond, the partial bond forming of the CC pi bond, and the partial bond breaking of the CBr bond. Yeah, so there's only one harm, there's no intermediates. Yeah, only first order reaction, that is SN1 or E1, will involve a carbocationic intermediate. Okay, so in this case, for the purpose of E2, over here it's written that the tertiary substrate is more susceptible for E2 elimination as compared to secondary, as compared to primary. Yeah, why is that the reason? Because remember earlier on, or maybe not earlier on, but under the chapter of alkenes, you learn that the more substituted the alkene is, the more stabilized the alkene is. Yeah, so in our case here, this is just a alkene, but this is what we call a mono-substituted alkene. So if we have another H being substituted, it's di-substituted, followed by tri-substituted, and followed by tetra-substituted. So the greater the substitution of the alkene, the more stabilized is the alkene, and therefore you would expect the transition state leading to the alkene to be more stabilized as well. Okay, so that might be something which you want to focus on, because in that case, right, the transition state will be so-called or resembles a more substituted alkene. Yeah, so that would attract a lower activation barrier, therefore a lower amount of energy is required, and that makes it more reactive towards elimination. Okay, yeah. So there is this little new term you might learn. I'm not sure whether it was introduced to you earlier on. This is known as regioselectivity. Okay, so in chemistry there are three kinds of selectivity that we often talk about. Okay, one is regioselectivity. Okay, so regioselectivity. Another one is known as chemoselectivity. Okay, chemoselectivity is sort of touched on in H2, but you were not taught the term. Yeah, but you do understand what it means. Immediately after I explain to you, you know what I meant. And then of course another one is called stereoselectivity. Okay, so for regioselectivity, we are looking at two potential elimination product, and then which product is more preferred. Yeah, so of course if you are getting the thermodynamic product, we will call this the ZTEF product. If you are getting the kinetic products, this will be called the Hoffman product. Yeah, so where will the H be removed from this particular substrate? Either the alpha product, the beta hydrogen, either HA or HB, will really depend on the nature of the base used. So I think second bullet point is trying to tell you that the ZTEF product is more substituted, Hoffman is less substituted. So one is thermodynamically more stable, the other one is kinetically more stable. Okay, so you would expect the activation energy leading to the more highly substituted transition state is lower. Okay, so the choice of the base is important over here. So for example, in this case, for tertiary butoxide, okay, you'll notice that in order for me to produce the thermodynamic ZTEF product, I need to abstract HB. Okay, but in order to abstract HB, right, HB is actually the sterically more hindered proton as compared to HA. Yeah, so if I'm going to use a bulky base, I expect the thermodynamic Hoffman product to be removed, to be formed slightly more readily. So the percentage actually now skewed towards the formation of the Hofmann product. Yeah. However, if I'm going to use ethoxide, relatively unhindered, yeah, then in that case, I probably expect more ZTEF product to be formed rather than the Hofmann product. Yeah, so that is what it means when we are talking about the nature of the base is important in the decision to whether we are getting Hofmann or ZTEF products. Okay, yeah. Then earlier on, I also mentioned about chemoselectivity. Yeah, so chemoselectivity basically is the difference in, let's say, oxidizing agent. I think the most clear-cut example for H2 will be oxidizing agents. You know that potassium permanganate, not only can they oxidize alcohols, but they can also oxidize alkenes, okay, and perform side chain oxidation for arenes. But potassium dichromate cannot oxidize alkene, cannot perform side chain oxidation. Yeah, so in some sense, potassium dichromate is more chemoselective as compared to potassium permanganate because it can only oxidize certain substrates. Okay, in this case, certain functional group, that is alcohols. And later on in under aldehydes ketones, you will also learn that, for example, the silver mirror test or the failing solution test for aldehyde. Yeah, so in that case, failing solution and Toland's reagents, the silver mirror test, right? Both of them can only oxidize certain kinds of aldehydes. So they cannot oxidize alcohols. So therefore, these two are even more chemoselective as compared to, let's say, potassium dichromate, because they are quite selective in the way they react. Yeah. I'm using a very generic way to explain. Of course, when you move on to university, you will learn that certain reagent prefers even certain kinds of alcohols as compared to others. Yeah, so that is even more chemoselective. Stereoselectivity, you will not exactly learn quite a bit in H3, but it's more related to whether a certain stereoisomers will form as compared to others. That is quite a generic view. So when we cover that, then I think we'll go more into details. Okay, so in this case, for the stereochemistry of E2, right? Yeah, in this case, you notice that there is this term we need to introduce to you, that is anti-periplanar geometry. Yeah, so that means that the CH group, right, when you look, let's say I place my eyes here, right? The HCCX, right, they must be in one plane. Yeah, so if I put a plane down here, yeah, all these groups must be in the same plane as the paper. Why is it called anti-periplanar? Because the H and the X are anti to each other. Yeah, so it is only when they are anti-periplanar that they can effect this particular E2 elimination. The result, and as to why that is the case, there's a MO explanation to it. We won't exactly go into details, but in short, what we are saying here is that number one is when a CH sigma bond breaks, right, at the same time it needs to form a pi bond, or rather it needs to lead to the formation of a pi bond with the neighboring P. Yeah, and also at the same time the electron density must be donated such that to the, I think in the MO term, to the sigma star of the CX bond, so that the CX bond will break. And when it's donated to the sigma star of the CX, in the process it leads to the formation of the pi bond. Yeah, so the only way where it can donate to the sigma star of the CX, right, is it's for them to be periplanar. Yeah, they must be in the same plane. If they are in a, imagine that if they are in a different plane, right, then the donation will not be effective. Yeah, they will not be facing each other. So that is the explanation why periplanar is important. Of course, without having an understanding of molecular orbital theory, without having learned it, right, then I think the simplest way is, okay, I need to form a CC pi bond, so they must be oriented in such a way that as the CX bond leave, the p orbital sort of develops, so I must allow the 2p orbital to overlap significantly. Yeah, so I think that's fine also. Yeah, so basically being periplanar allows us to understand why the formation of, or rather the breaking of the CH bond and the CX bond must occur simultaneously to the formation of the CC pi bond. Yeah, okay, but why must it be anti-periplanar? Why can't it be syn-periplanar? Well, the reason is related to what you learn under conformation analysis lah. So staggered conformation is more lower in energy lah, it's more stable as compared to eclipse conformation. Yeah, as what is shown in the diagram here. So I think with that you will probably understand a little bit more why anti-periplanar geometry is preferred over syn-periplanar geometry. Yeah, although syn-periplanar elimination is possible. Okay, so another way we call E2 is known as anti-elimination. So this is another illustration of the anti-elimination. Yeah, so there are a few ways you can draw elimination product depending on the nature of the question. Yeah, so one way is I think a very popular way of asking students to draw is to draw it in the Newman projection, which is shown here. This is a Newman projection, so you need to be able to draw it in Newman projection. This is a very popular way of asking question in H2, so just be aware of it. Another way where you can draw if they don't exactly ask you to draw a Newman projection is this particular manner, because in this manner I think it's very easy for you to arrange them such that they are anti-periplanar. Okay, so another way is this sawhorse projection, but this is not so popular, so this is not a very popular way of representing answers. Okay, so probably don't show it using sawhorse, although it's not wrong. Yeah, not to worry, the assessment, the exams will usually tell you how to represent your answers. Yeah, so usually it's Newman projections. Okay, yeah, so as I mentioned to you, syn-elimination is also possible, so under very special circumstances. Usually it's due to steric and geometric consideration. Yeah, so you notice that in our case here, anti-elimination is not exactly possible. Yeah, okay, so yeah, so because of that, then it will undergo what we call the syn-elimination, because in order for H and Cl to be anti-periplanar to each other, it needs to undergo some form of a ring flip, but this is not possible whenever I have a bridging hydrogen, or rather a bridging CH2 group. So in this case, not possible, so it will undergo the best other alternatives. Okay, which is in this case the syn-elimination. Yeah, okay, I'm not sure if this is okay, because okay, I don't know how you make sense of it, but can you, I mean, if I'm just going to sketch this out a little bit, in case some of you cannot exactly see, right? This whole geometry actually looks like this. So you have a H here, this is a H, and then you have a CH group, so I'm not going to draw that out, and then you have a deuterium. Okay, so that's a front view lah, right? And then the back, I'm going to use red. So for the back view, right, what I'm going to have is again another group attached like this. Wait, let me just try to check. Okay, and then another H here, and Cl like this. Okay, so I hope I get the direction correct. Yes, it's correct. Okay, now right. Okay, so under normal circumstances, right? I just try to say, let's say these two groups, let's say this is not fixed lah. I mean, just a random example lah. Let's say it's not fixed. Then technically, if I want to perform elimination, what needs to take place, right, is some form of a bond rotation to ensure that I'm going to get an anti-periplanar geometry. Yeah, so between the ClC, the CCl, and in this case the CH or C deuterium bond. Okay, so in this case I would expect something like this. So I'm going to draw it out. I'm going to use the correct colored ink. Okay, so I'm going to maintain this. This is deuterium. This is the H. Okay, and like this. Okay, so in most cases the rotation will take place such that, okay, I'm going to get like this, the Cl, okay, the H, and like this. Okay, if I'm saying if rotation is possible, Okay, I think you have to read into the context if rotation is possible. Okay, or I can rotate it further for something like this to happen. Okay, so sorry, I need to do some. Okay, this pen is not exactly working extremely well. Okay, so or I can do it, or I can do something like this. Deuterium H, okay, and then I rotate further H, and then the Cl. Yeah, can you see that, or can you observe that this is the anti-periplanar geometry I'm talking about? So this is the anti-periplanar geometry. Yeah, okay, that is if rotation is possible. But if my ring is being locked, okay, sorry, okay, if my ring is being locked up by the CH2 group, right, I can't be doing ring flip. Yeah, so I'm being forced in this in this particular conformation. Yeah, then in that case, what is the next best alternative? That will be Syn-elimination, right? So if I can't do staggered, I will do eclipse, no choice. But most importantly, they must be anti-periplanar. Yeah, because that is the qualifying criteria. Yeah, for elimination to take place. Taking into consideration what we understand about molecular orbital theory, that is, I think I've explained a little bit to you earlier on based on this particular diagram. But this is not an MO diagram because it did not show you much about what is required, so-called. Yeah, but to the best of our ability, let's say without 100% understanding what exactly is happening in MO, at least what we can say is that the breaking of the CH bond and the breaking of the CX bond, once they are broken, the two carbon now will take on sp2 hybridized geometry with p orbital, then they can overlap to form the pi bond. Yeah, that would be the simplest way. So because they need to overlap to form the pi bond, the geometry between the CH and the CX bond has to be periplanar. Okay. Yeah, so I hope I've made myself quite clear in this. Okay, and then here we're talking about stereo selectivity. The stereo selectivity here we are talking about is whether we are going to get whether one stereoisomer is preferred over the other stereoisomer. So in this case, we are concerned with whether we are getting the cis or the trans-isomer. Yeah, so so the discussion here, of course, we start off at the same point in the energy profile diagram. Yeah, but whether we get a cis or trans isomer really depends on the transition states. Okay, yeah. So here they are talking about the products, the interaction between, or rather they are saying that the trans product is more stable because of less steric demand between the methyl groups. Okay. Okay. Maybe I can explain it. I can explain a little bit here. Using maybe potentially using some Newman projection. Okay, so I think the first thing I want to do is I probably just want to decide on the stereochemistry. Yeah, because I think if I don't, it's a bit difficult to explain to you lah. So maybe can I just assume that the CBr is just projecting out, although it doesn't really matter because this molecule is symmetrical. Okay, yeah. Okay, so so first what I'm going to do is I'm going to label this as carbon number 1. Okay, just carbon number 1 and carbon number 2 lah. Okay, I'm going to draw a Newman projection. So the one in front is carbon number 1. Okay, then what's going to happen is that the methyl group will be pointing down, and then this will be the H, and this is the H. So this is carbon number 1, and then carbon number 2 is right at the back. Okay, so and since I have already defined, okay, let me see. Okay, maybe I should define it in a similar way, because let's say I put my eyes here, although it doesn't really matter because it's a perspective thing lah, but let's say I put my eyes here, then yes, carbon number 1 is here, then H and H. Okay, then if I move to the back, then this is the Br. Okay, and then this is the H, and then this is the CH2, CH3. So I just call it the ethyl group ET. I just represent ethyl group with ET, and then the methyl group with ME lah. Okay, yeah. So I just want you to notice one little thing over here. So in order for me, or rather in order for elimination to take place, maybe some form of bond rotation is required, but in this case probably no need already, because what I'm going to see here is there will be some steric repulsion here, but that is fine. So in this case, the anti-periplanar geometry is like this. Yeah, so you can see that upon elimination, then what's going to happen is that I'm going to end up with so if indeed elimination takes place, I'm going to end up with a product that looks like this. So I have oops, sorry, I need to change to the pen, back to the pen, right? Yeah, so upon elimination, I'm going to end up a product that is like this, the Me, okay, and then in this case the H, and then the H here, okay, and then the Et. Okay, so you realize that the methyl group and the Et, they are trans to each other. So trans meaning they are on opposite sides to each other. So that is fine. And you can actually easily tell from this particular conformation, because you can tell that the Me and H, they are opposite each other. So in this case, it's okay. Yeah. Then the other thing that you might be wondering is, can I do a bond rotation about the C1 and C2, so that in the process I will be able to get, say, a cis product, that is, yeah, a cis product. Can I do a bond rotation? Yes, I can do a bond rotation. So I can rotate this to the other way around. Yeah, but you need to take note of one thing. Okay, so I'm going to draw it here. If you do a bond rotation, right, this is what you're going to end up with. I'm going to have a methyl group here. Okay, I'm going to have a H. I'm going to have a H. So this is carbon number 1, right? Yeah. So if I'm going to do a bond rotation, the Br will be here, and then the ethyl group will be here, and then the H will be here. Now, what do you notice? Do you remember earlier on I drew this steric repulsion like this? Now I'm going to have two pairs of steric repulsion. Do you realize? Yeah. So although the C and the Br are in an anti-periplanar geometry, yeah, but number one is this particular conformation is not as stable as what we have earlier on. And then number two is that even if I'm going to effect elimination, right, I expect the transition state to be higher in energy, like this. It will be higher in energy. It's higher in energy because of steric, which is what I have represented here. Yeah, so that is exactly what it meant when we say that the transition state, right, leading to the product is actually more destabilized as compared to that leading to the trans product. Yeah, it's solely because the conformer to begin with is more unstable. Okay, so I hope that does help you understand a little bit about why the trans product is more favored as compared to the cis product. And this is the origin of what we call stereoselectivity for E2 reactions. Okay, then of course there is another term known as stereospecific, which honestly for H2 for H3 I don't want to go into detail, although I can actually have a separate video talking about this but I guess what we really want to say here is that for stereospecific reaction, right, what we want to highlight is that, okay, so in this case we have two chiral centers. Okay, we have one R2S, and then of course the enantiomer will be 1S2R. Okay, I'm actually talking about this. And then of course we have one R2R, and then the enantiomer will be 1S2S. So here what we are saying is that both 1R and 2S, sorry, both 1R, 2S and 1S2R, right? Okay, when I treat it with ethanolic KOH, yeah, what I'm going to get is the pure E product, and then the other one I'm going to form the pure Z product. So I mean just showcasing this to you is quite confusing lah. I mean, I'm sure, but what we really want to do is, because over here we have already performed an illustration. Okay, so I'm going to move back. Okay, so this is what we're talking about: one R2R and one S2S. Okay, so so the RR and SS is represented here. So if we simply just do okay, in this case we don't need to do a bond rotation. We can just perform elimination like this. So the base, okay, so the base, sorry, I think the pen is not working very well. Don't know why when it's at the top it will just scrambles. Okay, so when we have the base abstract push, so this is already in a anti-periplanar geometry. Yeah, you realize that whatever the case is, right, the two phenol group will be on the same plane. Okay, over here. Okay, they'll be on the same side. Sorry, not on the same plane. They'll be on the same side. Yeah, so that is why for RR and SS, right, they will only give rise to Z isomer. And then the same thing for RS and SR, right, they will only give rise to the E isomer. Yeah, so it will never be, there will never be a case where RR and SS sometimes can give you E isomer. No. Yeah, so this kind of reaction, right, where one specific stereoisomer is being obtained from a specific starting stereoisomers, right? This kind of reaction is known as stereospecific. So that is it is impossible for the products to scramble. Yeah, so if they scramble, then that means something is wrong with the mechanism. That means that mechanism is not pure E2, it could be something else. Yeah, so the term stereospecific is not the same as stereoselective. They mean quite different things lah. So do not use them interchangeably. Although in most cases they mean relatively similar things. Okay, so if we need more explanation, perhaps we can do a video on that. Okay, yeah. So okay, so I think over here, yeah. So for anti-elimination, yeah, this is what happens. So I think this is the same kind of Newman projection which we have showcased to you earlier on. Yeah, so for elimination to take place, yes, I'm getting this. Yeah, but is it possible for me to get the Syn-elimination product, which is the E isomer? No, it's not possible because it is too sterically demanding. Yeah, so therefore the Syn-elimination pathway is totally off. Okay, so this kind of reaction is known as stereospecific because the stereoisomerism of the product is dependent on the stereoisomerism of the substrate. Yeah, which is what I highlighted to you earlier on. Stereospecificity of E2 is only relevant when there is one hydrogen that can be abstracted. Okay, only one. Okay, so over here I also gave a remark. Stereoselective is another term, but it means differently from stereospecific, so don't use them interchangeably. And then now we are back to unimolecular elimination. I think you have heard me talking about it quite a bit. Basically, it goes through a carbocationic intermediate. Okay, now the thing about going through a carbocationic intermediate is that the CC sigma bond is freely rotatable. Yeah, and because it is freely rotatable, right? If you go by E1 pathway, it is possible for you to lead to product scrambling. Yeah, so which means earlier on we talked about E and Z, right? So you can have E and Z scrambles, getting a mixture of these products. Okay, yeah, so regio selectivity, regiochemistry. So E1 exhibits a good preference for ZTEF. Outcome cannot be controlled. Yeah, so thermodynamic product preferred. Yeah, so definitely not stereospecific. The reason is CC sigma bond is freely rotatable. Okay, stereoselective because cis and trans product both are possible, depending on which hydrogen is being abstracted. Okay, then we have a section on elimination or substitution. So again, we kind of highlighted it in activity 4. So a strong base prefer elimination, a large base prefer elimination as well. So a large base, large, steric, strong, right? So all this collectively we will call it a non-nucleophilic base. Okay, basically a non-nucleophilic base is a base which doesn't want to act as a nucleophile, okay, or is a poor nucleophile. Okay, so maybe let me write it out again. It's a non nucleophilic base. Okay, yep. Okay, I'll move on to the final bit where we have exercise 3. Yep. So in conformational analysis, a bulky alkyl group can fix the conformation of cyclohexane ring. Okay, so this is fixed. So in this case, because it is fixed, the cis-isomer where the Cl and the bulky group are on the same side, right, will give rise to the elimination product via E2. Okay, the trans-isomer cannot undergo ring flip. So you undergo a different mechanism, in this case a E1 mechanism. So because it undergoes a E1 mechanism, right, it can still give you the product. Yeah, because in this case, I do not need to undergo a ring flip to have anti-periplanar geometry. Yeah, and E1 mechanism tends to be a little bit slower because number one is I must have a condition where the CCl bond can break. Yeah, if the CCl bond doesn't want to break that readily to form the carbocation, right, then the elimination pathway will not take place. It is different from E2, where in our case here, right, I think in our case here, the Cl, C, C, CH are already in the anti-periplanar geometry. So already they are in such a nice arrangement such that E2 can take place. Yeah, so compared to E2, for E1, right, only the two-step mechanism can take place for it to undergo elimination, and for the first step, it will have to lose the Cl as a chloride to form the carbocation. And that step itself is really dependent on a few factors, like the nature of the solvent, the temperature also plays a role. Yeah, and of course the nature of the nucleophile. In this case, we are talking about the same nucleophile. Okay, yeah, so I think these are some of the considerations you need to have when you are discussing whether E1 or E2 is preferred or which is faster. Of course, without knowing without having more details at hand, like kinetics data, right, it is near impossible to say which is 100% faster or which is 100% slower. But you can actually make some deduction by understanding the nature, by understanding from the nature of the rate determining step. Okay, so there's also we have a 3.2.4 where we have a carbocation rearrangement. Yeah, so this is pertaining. Actually, this is not only pertaining to SN1 or E1, it's also pertaining to electrophilic addition, because all of these reaction goes through a carbocation intermediate. Yeah, so this kind of carbocation rearrangement take place in order to form a more stable carbocation. Yeah, so the driving force is the formation of a more stable carbocation. Yeah, so remember this. Yeah, so for example, in our case here, from a secondary alcohol, it gets protonated by HBr, so the OH loss is being lost as H2O, and then you form a secondary carbocation. So from the secondary carbocation, right, the first thing that could take place is a E1 mechanism where I will form compound A, and then the next thing that could happen is perhaps the bromide will then come in to form compound B. Okay, so this is normally what you expect from your current knowledge. Yeah, but sometimes we do get unexpected products. For example, we can get a methyl shift. So this is known as a methyl shift. So when methyl shift takes place, right, I form a more stable tertiary carbocation. And the more stable tertiary carbocation will lead to a more stable tetra-substituted alkene, as well as, and then in the process for SN1, I get this particular product, which need not be more stable than this. Yeah, but I think the point is the intermediate carbocation, being tertiary here, is more stable than secondary. So there is a driving force towards the formation of the more stable tertiary carbocation. Yeah, so that's something which you can take note of. Okay, and the carbocationic rearrangement has a very nice name known as the Wagner-Mervin rearrangement. Okay, and not only will we get alkyl group shifting to generate the more stable carbocation, there's also something known as a hydride shift. Why is it called hydride? Because essentially this H is shifts to the carbocation as similar to a hydride. Yeah, so if you look at the molecular orbital theory model, right, actually this is quite similar to our elimination process lah. So remember that for carbocation there's an empty p orbital, so this is empty. Okay, then in our case here, right, this is the sigma CH bond. Okay, the overlap. So this sigma CH bond, right, in some sense, right, it will donate electron density to the pi system, so that this electron density sort of get shifted, so that they change partner. So in the process of shifting, right, the transition state is that this particular carbon has a developing positive charge, but this particular developing positive charge is tertiary in nature, as compared to the other positive charge, which is secondary in nature. So in that case, the positive charge at the tertiary carbocation center is more stable than a positive charge at the secondary carbocationic center. Yeah. So this is the driving force for the rearrangement, secondary carbocation to a tertiary carbocation. Okay, and sometimes a tertiary carbocation need not be formed exclusively. So for example, in this case, this is a tertiary carbocation. Okay, but the alkyl shift can take place, which leads to the formation of a less stable secondary carbocation. But this need not be so-called less stable, because the tertiary carbocation above, right, has a 4-membered ring, okay, which has greater demand, steric demand, as compared to a 5-membered ring. Yeah, so this is known as a ring opening. Yeah, so, or ring expansion. So it expands from a 4-membered ring to a 5-membered ring. So such ring expansion helps to create a more stable carbocation species, despite it not being tertiary. Yeah, so I guess that's it for our discussion, because the next topic is on addition, which we'll cover in the next lecture. Okay.